Hello, my name is Davis Lester, and this is my Lab 3 help session. So there was a original problem with the recording, and so I'm going back through and explaining it once again for anyone who still has any questions. Let's go. All right, so this presentation, I'll go over some basic debounce logic and the circuits with the SR latch with NAND and NOR, as well as SPDT switch pinout function that I got a lot of questions on. And then we'll be moving into like the actual flip-flops, what you'll be using in the rest of the course with D, T, and JK. Then I'll do a counting example that can be similar to the actual lab. We'll do a next state truth table and we'll K-map that. And then I'll have actual implementation in Quartus. And then lastly, I'll do a 5-variable K-map. Okay, so the basic SR latch has a, hide this. There we go. Oh no. There we go. Okay. So the basic SR latch has two NAND gates or two NOR gates that have the outputs feed back into each other. So this allows to have hold, set, reset, and yeah, just those three functionality. So when S is true, or this input here, the input will be set, since we know that whenever S is true, it means it's set, so the Q output will be true here. And Q naught is just used to have an inverted version of Q, which can be useful for various types of scenarios. And then R is when R is 1, the reset will be true, which make the output 0. And now you do note that you can't have both of them as 1, or else this will cause various errors. So we write it as illegal in the table. Now we can expand this into a debounce circuit. So as you can see on the right-hand side, we have a basic SR latch using NOR, and on the next slide, I'll show you using NAND. So it's basically the same function. Then we have our SPDT. This is a little bit different of a image, but it's the same principle. And the switch is tied to voltage, and the resistors are tied to ground. Now, what this does is do note that the NOR gate version of the debounce circuit uses grounded resistors and the powered switch. What this does is it makes so that only one output can be true at a time. This Q here, I'll move my camera a little bit, this Q here, or this Q here, which will have an active high output since we are using NOR. So basically what this does is it makes sure that the output cannot bounce using the SNR because it can only be set and reset at individual times. Okay, so let's move on to the NAND gate. So the NAND gate is the pretty much exact same version of the SNR latch, but this time we use the resistors to VCC and the switch to ground. This will leave the same output, but we need to use the different versions because we have active low inputs. This way that we can still have the switch and debounce circuit to work. And you need to memorize this for your practicals, quizzes, exams. You need to know how to build a debounce circuit using both NAND and NOR. An easy way to remember this is that if you have NAND, your resistors go to power and your switch goes to ground. And the NOR version of the circuit is the inverse. And they both work the same way. And these circuits are useful to know because not only can you use them for debounce, but it's really nice to know how the actual SNR latch works. So now if we move on, I got a lot of questions in the lab about, or well, not even in the lab, in help session on Slack and in my office hours about these two switches. So I have the two switches shown. Not a lot of people have the switch on the left, and most people have the switch on the right, but the theory applies to both. So over here, you can see the switch has 4 support pins, or 2 grouping of support pins that actually don't do anything. They're just used to mount the switch to the breadboard. The actual switch applies down here or down here on the other switch. So the middle will be supply, VCC or ground. So if I'm using NAND, it'll be ground. And the 2 switch sides are the other pins. So make sure you route your pin sides to these down here and not the ones on the side, or else nothing will happen. So now we'll go into flip-flops. So flip-flops are extremely useful as you'll use them for a lot of state machines and counters. Now, you don't need to know what's going on inside the flip-flop, and in fact, it's pretty complex, but I think it's cool to note that every flip-flop has the similar S and R function on the right, but then I have some assortment of gates that'll allow for preset, pre-clear, and J and K and clock. So now the basic flip-flop, D flip-flop. I think this is the most basic one other than the T flip-flop because it's the most conceptually easy to understand. So how this flip-flop works is whatever you have come in as your D will be your output. So if we ignore these last three rows on the table, because those are about the presets and pre-clears, these first two, let's hit escape so I can annotate. So these first two rows here are useful because they're actually how the flip-flop will work. So I guess I messed this up here and it should be D. It should be D, but, oh wait, I went to the next slide. Uh, let's cancel these clear electrons and then to the previous slide. Okay, there we go. So if we look at only these two rows, we can see that when the input is 0, the output becomes 0. And when the input is 1, the output becomes 1. In this way, we know that the D flip-flop works, that whatever's going in will come out. So we can look at the next state truth table, and whatever we have as our Q plus is going to be what we route into D, which we'll use in I think it's part 3 of the lab. So this is extremely useful because it allows us to pretty easily make what's going into the flip-flop. However, we also have some active low signals here. So the preset and pre-clear, this diagram isn't really that accurate, but in Quartus, there's going to be a bubble here. So when the pre-clear goes low, it's going to make the output, I think this table is wrong. This should be a 0, and this should be a 1. So when the preset goes true here, because it's active low, it's going to make Q1. And obviously Q naught is just the inverse. Like I said before, Q naught is just used for different applications of the flip-flop. And again, when pre-clear goes to 0, it's going to make the output 0. And then again, like an SR latch, we can't have 0 and 0 for preset and pre-clear. So those same functions of preset and pre-clear will apply to the next flip-flop, the T, and the J and the K for that example. So here we have a little bit different of a diagram. This is the best one I could get. It doesn't have the preset and pre-clear, but in Quartus they'll be there. So the T flip-flop, similar to the D flip-flop, will work by having whatever is in T will cause it to toggle. So if T is 1, it doesn't matter what Q or not or Q was before, it'll be inverse. So let's say for an example, if I had 0 and we input a 1, after a clock signal, this 0 is going to become a 1 as it toggles. However, if we have a 0 and we have the input T of 0, the 0 is going to stay because they didn't toggle, which you can kind of see in the truth table here. So when it's 0, it holds, and when 1, it toggles. And then again, you have the same functionality of preset and pre-clear, that when you preset with a 0, it's going to make it a 1. I guess this table is also wrong. And when I have a pre-clear, it's going to make it a 0. Okay. So now let's go to the JK flip-flop. Now this is the biggest jump as there's a lot of people get messed up. Now, something that Schwartz says that I think is pretty funny is if you take a J, I'll make it like this, and you slowly, if I take away this side of the J, it kind of looks like an S. It'll probably look more like, let's do that. It'll look like this, which you can make it look like an S. And we can do the same thing with a K. If I take a K, kind of a bad K, and I wrap around this part of the K, and keep the bottom part, it looks like an R. So we know that J is like S and K is like R, which means that if I just write that here, S and R, we can see here, if J is true or S, it sets. And if K is true or R, it resets. So this is the basic and easy way to know how the JK flip-flop works, and it's how I always think about it when I'm designing my flip-flop or my counters. However, we also have 1, 1, and 0, 0. So the JK flip-flop, unlike a SR latch or SR flip-flop, you can easily learn that 1-1 is an illegal mode in the SR latch. But in the JK flip-flop, it actually has a functionality of toggling, which is extremely useful in a variety of functions. And then 0-0 will just hold. So now we can take this and then remember that the preset and pre-clear still works as before. But now I can clear and go to the next slide, and we can simplify this table to this. So this table is actually one of the most important ones that I would, if I were to remember anything. So we know that J is like S and K is like R. So if I have, for instance, Q as 0, right? Let's say Q is 0. And my Q plus is supposed to be a 1, right? So I know that I want the next state to be a 1, which means that we would ideally set it. So in a normal D flip-flop, actually in the SR latch, we would have S as 1 and and R as 0. Okay. So this is what we would normally do. But however, we're using a JK flip-flop, so we have the added functionality that we can toggle. And so if you look here, we're going from 0 to 1, which is actually a toggle, which means that S1 will stay as 1, but we can also have R be 1, because again, we can toggle, right? So now if we look at this, R can be 0 or 1, and you guys learned in class that if you have a functionality of an input being either options and the output remaining the same, we can have R be a don't care, Rx, which you can kind of see here. The set function, that's a horrible circle. But if we underline this row right here, if I'm trying to set the output, I can have S be true and R be, or well, J be true and K be an X. Because we can set the output either way by toggling. So now if I erase all of this, we can see the same thing applies for the reset function. So okay. The same thing works for the reset function, because if we're going from 0 to 1, we can, or sorry, from 1 to 0, we can just reset, but we can also toggle. So these two rows are extremely important because it allows you to be able to have added functionality, and this will make your K-mat simplification easier. Now, you could just say, if I wanted to keep uh, J at 1 and K at 0, but by using the don't care for K here, you're going to add simplification to your K-maps and your output equations, which is going to make everything a lot easier. So hopefully that explained JK flip-flops. That's probably the hardest thing for actually flip-flops in general. And so now I'll go into some questions. So I have this thought question here. How many flip-flops are needed for this counting sequence? So a lot of people, in fact myself as well, got originally tripped up. So I have the decimal count and I have the binary count right here. So it goes 3, 1, 2, 0, 3. So this count uses if I were to represent all of these bits with the count, we would only need 2 bits, right? But that's what a lot of people go wrong. See, because this counter uses everything based off of states. So if we look at this, annotation, perfect. So if we look at this, we have 3, 3, 1, 2, 0, 3, right? So this count has 4 states. You look at it, we have the 0 state, the 1 state, the 2 state, and the 3 state before we go back to the 0 state. So to figure out how many flip-flops a counter needs, we look at the highest number of states, which is 3. And we know that 3 in binary is 1, 1. So the most amount of flip-flops that we need would be 2. 2 flip-flops so that we can represent the highest bit and the lowest bit here. And we can see that here too. So now if we go to the next slide, can I clean this? Okay. you can see that I have another count form here. So I say, okay, let's count 37, 60, 22, 4, and 37. Now I represented these in 6-bit numbers because the largest bit is 37. Now we could say 4 is just 1, 0, 0, but I added the front zeros to be clear. So now try and go ahead and do this problem in your head and pause now if you want to try it. Okay, so again, if we look at this, the amount of states, we have a 0 state, a 1 state, a 2 state, a 3 state, before going back to a 0 state. Now, this is a little bit more advanced than what's going to be in your lab, but I think it's important to learn it now before you get too late and you're questioning your knowledge. So again, even though I tried to trick you and have the amount of bits here, even though there's 6 bits, we actually only need, again, to represent the highest number of states using binary. So again, 3 in binary is 1, 1. Let's add a base 2 here so that no one forgets. And we just need to represent this number and this number by flip-flops. So again, we can look at the answer, and it would be 2. So again, this is probably not necessary for this lab, and you'll probably not use it for a while. But it's good to know now because it's probably going to be something you'll see on the exam. Okay, so okay, that has all that I wanted to go over with flip-flops and counters. So let's actually do an example of one. So I say, let's make a counter that counts 3, 1, 2, 0, 3, using a D flip-flop as the most significant bit and a JK flip-flop for the least significant bit. So the first thing you always need to do in a counter is write down the count sequence properly. So when I was doing this help session in person, I wrote down the count sequence properly, and all of my answers that I had were wrong. And actually, I think yeah, so always make sure that you have the count sequence written down properly so you know how big it's going to be. So let's jump. And so now, like I said before, the first thing that you always do after that would be a next state truth table. So let's go ahead and I'm going to do my next state truth table in Excel because I think it's the easiest way to do this. So let me just open up Excel here. All right, let's share my screen. Okay, so the count was, if I check in PowerPoint real quick, the count is 31203. Okay, so let me just write that down. 31203. Okay, so now, like, the biggest count is going to be 3. So that means we're going to need 2 bits to represent it. So we can have Q0, or I'll write Q1, and then Q0, and then Q1 plus, and Q0 plus. So this represents our next states. We said also that we're going to have a D flip-flop for the least significant and a JK for the most significant, or well, D for most significant, JK for least. So I'm just going to go over here and make these centered so it looks a little bit nicer. And then add some columns. Actually, okay, let's go here first. So truth tables are always in counting order. So even though Q1 plus and Q0 plus are probably not going to be in counting order, we should keep Q1 and Q0 in counting order. So we'll do 0, 0, 0, 1, 1, 0, and 1, 1. Because this represents the biggest amount of states that we can have. Or well, this represents the states. So after this, our next state, so we have the count of 3, our next state would be 1. So I just go to the row with 3, and our next state would be the 1 state, which would be 0, 1. So I can just write 0, 1 in here. So you can see that after 3 comes 1. And then after 1 comes 2. So I would put 1, 0. So that in the 1 state, what comes after it is 2. And then after 2 comes 0. So I put 0, 0. And then after 0, 0 comes 3. So I put 1, 1. So let's add some little lines that can help us visualize how this table is broken up. Left border. Same here. And here. Okay. So now that we have this is the main part of the truth table, as it represents how we can go from this state to the next one. So now let's go ahead and figure out what we need for D. A lot of people that I got questions on when they're doing this lab is they didn't include this part here, and they only had their Q1 and their Q1 plus. While it's okay that you can route this Q1 plus straight to your truth table, or well, K-map, and then write that to D, that's not exactly what we need to do. And we need to think about it logically, because when we go down the line later, your Q1 plus is not always going to be what you route into your flip-flop. Now, for the case of D, we do look at Q1 and Q1 plus because it's our most significant bit. And again, remember what I said earlier, the D flip-flop, whatever goes in, will come out. So if we want 1, we just route 1. If we want 0, we just route 0. So in this case, for this very specific case for the D flip-flop, your Q1 plus and your D should be equal. However, for every other case, you would not have them equal. So let's look at the Q0 plus. So now we have to look at our least significant bit for our JK. So if we go from a 0 to a 1 in here, we can actually ignore all of this for Q0 and Q0 plus. That's all we care about. I'm going to put a little highlighting so that you guys remember. Oh, well, I can remember what I'm looking at. So if I'm going from 0 to 1, then that means that we need to set it. So we'll keep J as true. Remember, J is like S and K is like R. I'll just keep these here so that we can remember. So if we're going from 0 to 1, we can set like with the 1. But if we go back to the PowerPoint, I guess I need to stop sharing and share my entire screen. If we go back to the PowerPoint, right here, you can see with the JK flip-flop, if I'm trying to set it, we can have 1 or X. Why did it go away? Let's go back to Excel. So we can have 1 or X because we're setting it. Remember, you can have 1 and 0 or 1 and 1 to toggle. Now let's look. So we have 1, we go to 0. So that means we reset. And again, we can have the toggle functionality because we're changing both of them. Okay, so now we have 0 and 0, and we want to hold. So we can either represent, we have to represent that as 0, 0. And same thing for this one, 0, 0. However, another trick that we can use is the fact that you're effectively resetting it, right? Whatever this is here, we want our output to be 0. So K can also be 1, or R can be 1 because our output will be 0. So we have 0 or 1, so that means we can have 0x. Now here we have 1 and 1. We want our output to be 1 eventually. So while we could use 0 and 0 to hold, we also can have S be 1 because we can have it set the output bit. So that can have our S be 1 or 0, which means we can have an X there as well. So this should be our finalized truth table. No fill and no fill. So this should be our finalized next state truth table. And this is how we would end up being able to figure out the equations for the actual inputs for the flip-flops. So now that we've figured out these here, we need to figure out them as a function of Q1 and Q0. Now, I like to say as a function of Q1 and Q0 because I had some people come up to me and say, hey, I'm doing my K-map as with Q1 and Q1 plus as the inputs. That's not how this works. The circuit can only look at what you currently have, which is the Q1 and Q0 state, to determine what you can put into the flip-flop. Now, I could say that I want to look at the outputs and do logic to go back into the input. However, that's generally frowned upon as it's not as I guess it's just not good technique. So I'm going to look at Q1 and Q0 and determine the equation that's going to generate D0, D. So I'm going to swap over to Chrome because I have a nice little whiteboard. So I'm going to do, I may not be the best with the pen on the computer. I'm using the trackpad, but I'm going to try. So if I have Q1 on the vertical axis and Q0 on the horizontal axis, for my K-map, I can have 0 and 1, and 0 and 1. So I'm going to draw it like this. And you might have seen this version of how you draw a K-map before. In fact, I think it's probably the easiest way. So you can kind of see that I'm separating them. So if I look at the operation, so this is for D. That's a terrible D. D. So if I look back, we know that it goes 1, 1, 0, 0. So in the 0, 0 state, it's 1, and in the 0, 1 state, it's 1. So I just like doing this is by saying if I have Q1 on the vertical axis, oh sorry, Q0 on the vertical axis, Q1 on the horizontal axis, the truth table in order is going to 1, 2, 3, 4. Like 1, 2, 3, 4. So it would be 1, 1, 0, 0. Okay? So this is the K-map, and I think we all can pretty much see here, with K-maps, you try to make the biggest circle of ones. So I can see these two, which is a pretty easy circle. And because Q0 is changing, right? Q0 can be both 1 and 0, we can ignore it for the output, which means that the output would just be Q1 naught. Q1 naught equals D. So in Quartus, now I can just take Q1, invert it, and put that into the D flip-flop, and it's going to generate our next state. So let's do, I wonder if I can copy it. I guess not. So let's do this again for J. That's a pretty bad J. J. So Q1, Q0, 0, 1, 0, 1. Let's draw this. Might have some curved lines. Okay. Bam. All right, so let's look at the truth table again. So for J, we have 1x, 0x. And again, if we use the technique that I showed, you have, what was it? 1x, 0x. You write a 1, and an x, and a 0, and an x. So another thing that's very important that Schwartz would like you to know is that we can treat don't cares as both zeros or ones. So if I treat this x as a 1, that means that we can have a circle here, right? But if we had the x as the 0, we would not end up with the same equation. So do know in the practical and the exam, anytime you see the question, if we were to change the x, the don't care condition to be different, would it result in the same question? The answer is no, because our circle would be different. Excuse me, our circle would be different for the K-map, resulting in a different output equation. So for K, or sorry, for J, we can just use the same equation. So Q1 naught equals J. Now we can do one final K-map for K. I'm not going to go in depth with this one because I already did it twice. Q1, Q0, 0, 1, 0, 1. Okay. And we look at it as x1, x0. So x1, x0. And again, I guess I can route the same thing. So if I make this x at 1, I can do a circle here. And I guess all of them are just Q1 naught equals K. So let's go back to make sure. Let's just make sure that we had our states correctly. So 3, 1, 2, 0, 3. So 3 goes to 1, 1 goes to 2, 2 goes to 0, and 0 goes to 3. All right. So now that we have these K-maps, all of them are Q1 naught, we can open Quartus. I actually don't have Quartus open, so let me open that real quick. I prepared a little demo. So, thing to note is that when you're doing your K-map for larger than just two variables, be sure that you reverse the actual output. So remember that it goes 0, 1, 3, 2, because without that, then it wouldn't actually what's it called? It wouldn't actually output anything. Or well, the K-map doesn't work because the way that it works is that you have, if I had 0, 1, 2, 3, the bits would change in both ways. Here, let me show you this on the whiteboard because I think it's actually pretty important. Whiteboard. Okay, so if I had 0, 0, 0, 1, 1, 0, and then 1, 1, right? When I'm going from this one to this one, we only change the first bit. But when I'm going from this one to this one, we change the first bit and the second bit, so it won't work. So you have to do 0, 0, 0, 1, 1, 1, 1, 0, so that when you're going between each step, you're only changing one of the bits at a time, so that the simplification is actually going to work. See, we change this bit, change this bit, change this bit. Okay, let's go to Quartus. So we're back in Quartus. And this is what it looks like. I ended up recording part of this uh, without the screen sharing, so I guess I'll go back over it. So we know from the equations that we have just not Q and Q1 as our inputs for the D flip-flop, the JK flip-flop for both of them. So I just have a simple inverter gate. And then we have the start active low. So another thing is you need to make sure that you have start active low going into the preset, or well, yeah, the preset for this flip-flop, because we always want to start at the first state. So if we look back at the question, it says to start at 3, which means that we need to have the initial start active low initialize the counter at 3, which means we have 1 and 1. Since remember, the D flip-flop represents the most significant bit, and the JK flip-flop represents the least significant bit. Okay. So let's continue. So how this works is we have VCC going to the opposite, so that pre-clear is never going to be true. And make sure that you have, why are you going? We have Q1 and Q0 always as outputs, because if we have them as inputs, Quartus is going to give us an error. And why would we set the state bits? Because the counter is just me counting through them. We have clock and start as inputs. And so basically how this works is in your exams, practicals, wherever, when you're going to go and draw a functional block diagram, you wrap around Q1 coming out of the flip-flop into some sort of mystery functional box that does logic. In this case, we just have a simple inverter gate, but in other times you're gonna have some complex logic, and you come out, and that's gonna go back into the flip-flop. Now, like I said before, I have logic going out of it from the current state in the next state, because our next state would be going into the flip-flop. But you alternatively could have logic going on this side, where you have logic from the next states into the current state, but you can't really do that, and it's frowned upon. So always have the outputs come out, go into logic, and then go back in, which we have here. So if we go back to the simulation, I showed everyone that you usually have hierarchy. Make sure that when you're compiling, you have your top level entity selected, and then you go to files to be able to select your waveform, and I can just open that up. Okay. Hello, everyone. This is the third time recording this because it doesn't like to save. So right now I have the simulation pulled up for the course that I had from before. If I open the PDF, you can see it's all the same. So basically what you have is like I said, I guess you didn't know, but so to have the start function, I just set it to high, right? And then I just have the first part be low for a little bit, because since it's active low, if we only have it low for a little bit at the start, it's going to set it to the known state that we need, and the rest we can have just be free. Now for clock, you guys know how to do this. You just clock it. I do every 25. It doesn't matter. You can do 10, but you just need some form of a clock to count the counter to the states. Now there's this cool trick you can do with the outputs. Is when I'm grouping them, I can group them as like count, and then keep this as unsigned decimal. So we count in our human world as decimal numbers. If I were to use signed decimal, it would think Q1 would be negative or positive. So having it count in this way means that when we simulate it, it's going to display the count that we want. So 3, 1, 2, 0, if I remember correctly. Yeah, perfect. So there we go. And we can have our outputs displayed, which has everything that we need.
I assume that's how it applies. I didn't know for sure. Yeah, I didn't know for sure.
We actually are able to check that it works. So with this in mind, that's just all we needed for the counter. It's pretty straightforward. When you have bigger counters, obviously you're going to have bigger logic. And always, like I said before, make sure that you have your outputs be um, your state bits be outputs, because if you have inputs, that doesn't make much sense, and Quartus will give you an error. Now, if we think back to that example that I had before, right here, this one, where we have special counts, and I said you only need 3 states. So we can actually use this counter, well, not this counter, but we can have, wait, did I only share Quartus? Let's go back to Zoom, make sure about this. Wait, I swear it was like this. Okay, whatever. The count was, why isn't it not? Okay, it went away. Um, Okay, so I only shared Quartus, that's fine. Share Quartus, next share. Why is it not doing it? Okay, we'll share the entire screen. Okay. So if we look back at the PowerPoint, you can see that while it's not technically correct and we would want to increment our states 0, 1, 2, 3, how this would work in Quartus is, let's go here. You would have conditional logic on the Q1 output. So I could say and 2. So if I have in the first state, let's say I just have an inverter gate. So Q1, not Q1, and then I had an inverter gate, and so I could have not Q0 as well, right? We would have this certain bit as it would be true. Oh, well, I guess we would need a NAND. NAND 2. Or well, yeah, NAND 2. So that 0, 0 would be 1. I could have an output, let's say, like bit 0. So, when it's in this state, we can have a special output of bit 0 be true. And I can do this a bunch of times so that I can have 6 bits. And the logic here, this is just some simple logic, but I can have 6 bits. So our counter only has 4 states, but counts in 6-bit numbers, which is going to be pretty useful down the line when you design some more bigger counters, or on the exam. I think there's a lot of questions like that, and even on the what's it called? I think it's lab 5 is when you do the traffic light controller. So let's go and do a 5-variable K-map. So I ended up making, let's go back to here, actually. So I made this here, and I think that it would be good for you guys to know how I would do this, because a lot of people mess up on 5-variable K-maps, and it's pretty easy to mess up, and it's actually hard theoretically. So the best way I think to visualize this is using a 3D space. So if I have a K-map here, right? K-map, let's draw some rows. This is like if I was looking down at my paper or something like that. So we have some 1, 0, 1, 0, etc., right? Oh, this is just a 4-variable, right? A 5-variable works by connecting this K-map across the 3rd dimension into another one. So we'll have K-map 2 right here. I guess that's a pretty bad drawing, but we'll have what's essentially like a cube of K-maps. So again, 1, 0, you get the gist, right? But how this works is in this bottom K-map here, we'll have, let's say, we'll choose one of the outputs. I'll say E. So we'll have be E true, E equals 1. And the top K-map will have E equals 0. You can choose any of these. In fact, it's probably more advantageous for you to use A, which is your most significant. But I just did E for this example. So in this way, we can have E equals 0 and E equals 1. We can circle across or through the K-map. Because remember how K-maps work is you're circling across things so that you can reduce the amount of variables. If I have something that's true, let's say this 0 was a 1. This 0 was a 1. Pen. 1. It would be true for both of these values, and we can eliminate the E from that term. So that's extremely useful when we're going into understanding how K-maps work and just overall. So let me get out of this PowerPoint, and I'm going to copy this. Let me clear the annotation. And I'm going to copy this into Excel because the K-map is nothing but a table. And stop share. Paste as plain. Paste as plain text. Perfect. Okay. So a K-map is nothing but a fancy table. So over here, I'm going to have two variables going down and two variables going across. So I'll have B, I'll have A, B, B, C going down, and then I'll add a backslash, and then D and E going over. So remember, like I said before, we need to do the special format do this as text. So 0, 0. We'll just do a bunch of area. Okay. So 0, 0. Remember the order that I told you from before? 0, 0, 1, 0, 1. Oh no, I even messed up. 1, 1, 1, 0. And then we'll do the same thing across 0, 0, 0, 1, 1, 0. As we only want one variable to change at a time. I'll just select all of these. Clear the error. I don't know why Excel does this, but so we'll have these, and so this table will represent. I'll just merge these. This is when A equals 0, and then we'll do the same thing: 0, 0, 0, 1, 1, 1, 1, 0, and this is when A equals 1. A equals 1. So I'll draw a line right here so you guys can see top board. So now obviously this would be, excuse me, faster if I had pen and paper. But I'm just doing this on Excel because I don't have a stylus to write with. Okay, so now I'm just going to go through and look at each term. So the first term that I'm going to look at is the last one, A naught, B naught, C, D naught, E, as that one has all the variables in it. So I'm going to look. So it's A naught, so it's going to be in this half. B naught, so it's one of these two. C, so it's going to be this row somewhere. And then it's D naught E, so this one. I'm going to put a 1. So this represents this last term, so we got that one done. Now we can look at this one. A, B, C, D, E also has all of them. So we have A true, B naught, so it's going to be B naught, and then C, so it's going to be somewhere on this row. And then we have D and E both true, so that's going to be a 1 here. So now we have these last two true. We're going to look at this term. So A naught, C naught, D, E. So this actually is missing a B term. So that means that it's going to happen when both B is true and false. So I'll look A naught, C naught. So C naught is these two rows, C naught, and then D naught E. So D naught E is here. So I'm going to put a 1 here when B is false and a 1 here when B is true. So that represents that equation. So now here we have B naught, we have B D naught. So that's going to be everywhere that we see B D naught. So B would be true here, and D would be false, false here. So B, D naught would be D's corresponding 4, because we have B true and then D false. So I'm just going to write a 1 in all of these. But notice that we already have a 1 in this right here, so we can just leave that one there. Now we're going to do, so that's when A is false. So let's do the same when A is true. So all 4 of these are going to get 1. Yep. So all 4 of these are going to get 1. So now let's look at the last one. So ACE. So this is missing a B and D term. So that's going to happen when B and D are both 1 as well. So let's look. So A has to be true, and then C has to be true. So in one of these rows, and then E needs to be true. So that's going to be these 4. So again, notice that we already have 2 of the 1s. I can just put a 1 here and a 1 here. So now that we have that done, let's highlight all these and remove the errors so it's just easier to see. So what we can do now is we're gonna do our circles. So the first thing that we want is we want to make the biggest circle. So I want to look for a circle that's gonna represent. Oh, first we need to add zeros the rest of the columns because that's when the equation is 0. So now, in a perfect world, you would look for you would count whether or not there's more zeros or ones. But for me, I'm just gonna say we're required to do ones, so I'm gonna do those first. Let's add some borders. Bottom, so you guys can just see this a little bit easier as I'm doing it in Excel, which is an unconventional way. No border. Okay. Um, okay. So I want to circle as many as possible. So I see this here, I see this here. But another thing is that you can circle through them. So both of them share this 4 here. So that's going to be a dead giveaway. I guess I'm just going to use highlight for the time being. I'm going to use yellow for all of these. So that's going to be a circle there. Now I want to look and see where there's more. So there I see a 4 here. So I have this cell and this cell. Oh, these two that represent like a stacked 2. That can be 4. But I also see, oh, I see a circle here with these 4 in a line and these 4 here. So I think that it's going to be easier to include these two to draw these circles separately. So the only 3-dimensional circle that I guess we'll have is going to be this yellow. So I'm also going to draw a circle here. So I guess we'll do red for this, red, and then that way when these two are highlighted, they will be orange. And then I'll do blue for these, blue. So that when it's double highlighted, this will be green. Okay. So hopefully that makes sense. So now I'm going to do the yellow, like 3-dimensional highlight. So when we're looking at the yellow, we see that D is always 0, but E changes. So we're going to write the D as being false. So D, not D. And then I'm going to look and see here. So A changes, remember, because we have that 3-dimensional. So we can ignore A. And then through here, we have C changing from 1 to 0. So we can ignore C. But we can going to keep B. So that means B will be true. So I'm going to add a plus because we're doing OR. So now I'm going to do the, what's it called? I'm going to do this red highlighting, or I guess it's also orange because we double circle these bits. So I'm going to see that, so A is 0, so it's going to be not A. And then for all of this, we have D and E. D false, so not D. And then E is true, so E. And then we don't care about B or C because it's true for all of them. So let's go to the next one. So let's do the blue circle or also green. So that's going to happen only when A is 1, so A. And then it's going to happen when there is, so we see that it's between these two. So that's when D is changing, but E is 1, so we'll do E. And then this is also when C is 1, but B is changing. So we have C is 1. So we'll write it in numerical order. So it is not, it is like this. But remember, for alphanumerically, nots come before trues. So it would be not A, T, E, or not A, C, E, or not D, B. So this is our final equation. Now we can see there's some similarities, like not dB is right there, and then ACE is right there. But we were able to remove some of the extra equations from there, which caused us to get our final equation to be this. So this is probably not the best in value as you get as an input, but you'll get something similar to this where you'll have a truth table and you'll get outputs that you can represent in the K-map, and you'll get your final answer. So that's all I had for the help session. If anyone has any comments, please let me know, and I'll probably be doing a help session for the rest of the labs. So thank you and good luck on lab 3.